Spring Boot wins this benchmark, but the useful part is not the scoreboard alone. Go and .NET both accepted traffic they could not actually finish, and that is why this video starts with the contradiction instead of with setup. Before any framework gets credit, the fairness contract matters. Same orders endpoint, same event shape, same Kafka broker, same PostgreSQL sync, same retry budget, same host limits, and the same normal spike and slow database scenarios. Why does that matter in production? Because a fast accept path is fake comfort if the queue quietly becomes debt. A service can keep returning accepted while the consumer falls behind badly enough to turn success dashboards into lies. The project tree shows that this is one benchmark system, not three unrelated demos. There is a tiny wrapper entry point, one experiment runner, one set of fairness documents, 3 implementation lanes, and 1 artifact trail that records what actually happened. That tiny wrapper script matters because it proves the entry point is boring on purpose. The root command simply hands off to the experiment runner, which means the real benchmark behavior lives in the project and not in hidden shell glue. The spec file is where the benchmark becomes concrete. It pins the targets, the runtime, the payload shape, the fairness controls, and the scenario ladder. If you want to know whether the result means anything, this file is the first serious answer. The fairness policy is the second answer. It states that all 3 lanes must expose the same functionality, use the same dependencies, respect the same workload limits, and report failures instead of hiding them. That policy is why this is a benchmark and not a marketing stunt. The compose file makes the runtime topology explicit. Red Panda, Postgres, the runner, and the 3 target services all sit in the same environment, with the same shared infrastructure and the same lane-specific environment variables for topics, ports, and database connections. Once the infrastructure is visible, the runtime architecture is simple. The load driver hits the target API, the API produces into Kafka, the background consumer drains into Postgres, and the runner writes traces and metrics artifacts that tell us whether accepted traffic turned into completed work. The scenarios are not filler either. Normal load asks whether the lane behaves honestly under steady pressure. Spike 10x asks whether the API is just outrunning the consumer. Slow database asks what happens once the real bottleneck moves behind Kafka and into Postgres. The Python benchmark engine starts by declaring the directories, the targets, the scenarios, and the execution profiles. That matters because the benchmark is not improvised at runtime. The lane list and the pressure ladder are fixed in code before the first request is sent. The next part of the engine is the operational core. It builds the images, starts the shared infrastructure, launches one isolated target container per scenario, assigns unique topics and consumer groups, and drives load through the same HTTP surface for every lane. Then the engine turns execution into evidence. It persists partial results while the run is still happening. Writes request traces and runtime snapshots, and only then aggregates the final report. That is why we can inspect accepted counts, process counts, lag, and retry behavior later, instead of trusting a single terminal line. From the operator point of view, the run begins with infrastructure hardening, not with a pretty chart. Kafka must become healthy, Postgres must become healthy, and the runner must stay clean before any target is allowed onto the field. The Go lane startup tells you what it wants to be. The HTTP server binds, the broker connects, the consumer group subscribes, and the metrics endpoint exposes produced, processed, and estimated lag. The lane presents the exact truth surface we later use against it. The Spring lane startup is more verbose but not more magical. Tomcat comes up, the health endpoint answers, the Kafka listener subscribes, the database pool becomes ready, and the retry plus dead letter path is armed before the load begins. The .NET lane startup follows the same pattern. Minimal API binds, the hosted background consumer starts, producer acknowledgements stay strict, autocommit stays off, and the metrics endpoint exposes the same backlog truth surface as the other lanes. That shared API contract is intentionally boring. Every lane must expose the same post orders route, accept the same payload, return accepted with an order ID and trace ID, and then prove later that the accepted work really finished. After acceptance, the intended runtime path is also identical. Driver to API, API to Kafka, Kafka to the background consumer, consumer to Postgres, then process signals and metrics snapshots. The benchmark only matters because this expected path is comparable across all 3 lanes. The Go source makes the risk visible immediately, the handler accepts and publishes, the consumer loop retries and can deadletter, and the metrics snapshot computes estimated lag from produced minus processed minus DLT. In other words, the Go code itself exposes the exact truth we later use to judge it. The Spring controller is intentionally unglamorous. It validates the payload, stamps IDs and timestamps, publishes the created event, and returns accepted. That boring symmetry is the point because the controller code is not where this benchmark gets won. The Spring consumer is where Spring earns the verdict. The retry loop is explicit, the dead letter path is explicit, the database write is explicit, and the latency accounting is explicit. The code that matters most is the code that proves the queue actually drained into the database. The .NET lane follows the same general architecture: minimal API for acceptance, hosted background service for consumption, explicit Kafka commit behavior, and the same database write path. That symmetry is useful because it lets us compare outcome quality without pretending the workload model was different. By the time the live metric snapshots arrive, the winner is already visible. Spring has produced and processed the same amount under normal load. .NET is behind, but still plausible. Go has accepted a full lane of traffic and converted only a tiny fraction into completed work. That is why the normal scenario matters so much. Normal load should have been the easy case. Instead, Spring drains cleanly. .NET starts borrowing from backlog, and Go immediately disproves the comforting story that a fast API alone means a healthy system. The spike chart makes the production trade-off obvious. Spring pairs zero lag with low P99.NET, and Go pair enormous lag with catastrophic tail latency. That is not a small optimization difference. That is the difference between draining work and letting debt stack in Kafka. The slow database chart is the fairness stress test. Nobody looks clean once Postgres becomes the choke point. Spring still pays tens of seconds at the tail, but it pays less than the others and preserves more control over backlog. The artifact file is where the benchmark stops being a code tour and becomes measured truth. It records the methodology, the selected targets, the selected scenarios, and then the accepted versus process counts for each lane. This is where the API story loses to the completion story. Once the artifact is on screen, the final scenario ranking is no longer a matter of taste. Spring wins normal, wins spike, and remains least bad in slow.gb.net. Stays behind Spring, Go falls behind earliest and farthest. So the final decision stays narrow and practical. For this Kafka plus Postgres order pipeline, Spring Boot is the safest default because the source code and the artifacts both show it preserving Q-truth best under pressure. .NET is salvageable if you want to keep investing. The Go implementation, as benchmarked here, needs redesign before it deserves production trust.